So I want you to just think for a second about the electronic key fob that you probably have sitting in your pocket, or maybe it's like on your kitchen counter right now.
Oh, yeah, the little plastic thing for your car.
Right, exactly. You know that little piece of plastic that you just press to unlock your car doors? And it is something you likely use every single day, completely without a second thought. But I want you to hold that object in your mind for a minute because humanity's farthest reaching and, most extraordinary space mission was launched with literally less computing power than that little piece of plastic.
It really is wild. It frames the reality of 1970s engineering in a way that sounds almost completely impossible to us today.
Yeah.
Because, when we think of interstellar exploration now, we immediately imagine supercomputers and like artificial intelligence, not technology that predates the home personal computer.
Exactly. So, welcome to today's deep dive. Today we are tracing how two machines, Voyager 1 and Voyager 2, managed to pull off what is basically the ultimate cosmic road trip using that exact primitive tech. We've got this beautifully written essay detailing the mission, and our goal today is to really unpack the brilliant engineering, the undeniable cosmic luck, and the poetic legacy of two small robotic spacecraft that are still somehow calling home from the absolute dark.
It's such a great source text, too.
It really is. So I invite you, the listener, to just settle in, set a warm, unhurried pace for yourself today. We need to travel all the way back to 1977.
Ah, the 70s.
Right, an era of bell-bottoms and 8-track tapes. Mobile phones do not exist at this point. And from that baseline, we are going to follow the Voyagers out into the void.
Yeah, and establishing that 1977 context right away, I think, really highlights the central engineering problem of this entire endeavor.
How so?
Well, we are talking about spacecraft with incredibly limited computing brains, sure, but they also had these severe constraints on physical power and fuel.
Right. They're tiny.
Exactly. The engineers couldn't just, strap a massive rocket engine to these probes and hit the gas for decades. So the logical problem immediately becomes, how do you get a spacecraft with a tiny little fuel tank to cross the entirety of our solar system?
So if I'm understanding the physics of this correctly from the essay, they actually weren't relying on their own engines to travel billions of miles. The source mentions this really rare opportunity called the Grand Tour, and that relied on a specific alignment of the outer planets.
That's the crux of the whole thing, yeah. In the late 1970s and early 1980s, the four giant outer planets, so that's Jupiter, Saturn, Uranus, Neptune, they all happen to line up on the exact same side of the solar system.
Which is pretty rare, right?
Oh, incredibly rare. You have to remember that these planets are all moving at vastly different speeds in these massive, sprawling orbits. They do not sync up often. This specific geometric configuration, where they're basically in a row, only occurs about once every 176 years.
Wait, 176 years?
Yeah.
Meaning, if NASA missed this window in the late 70s, there is literally no second chance for anyone alive at the time.
None.
You just have to wait the better part of 2 centuries for the planets to align like that again.
Precisely. So NASA astronomers realized that because these giants were lined up, a single spacecraft could, theoretically, visit all four in one continuous journey. But to actually make that leap from one planet to the next without just running out of fuel, they had to execute this maneuver called a gravity assist or a slingshot.
Okay, here is where I want to push back just a little on the terminology in the essay, because it describes the spacecraft as stealing speed, quote, entirely for free, no fuel spent, end quote.
Ah, yes.
And my understanding of thermodynamics is that you cannot get something from nothing. If the spacecraft is suddenly accelerating toward the outer solar system, that energy has to come from somewhere, right? Is it literally stealing Jupiter's orbital momentum? Does a giant planet actually slow down?
That is a really highly perceptive question, actually. And you are entirely right to challenge that idea of free energy.
Okay, good.
Because it isn't magic, it's a strict mechanical exchange. When the tiny spacecraft approaches Jupiter, it falls into the planet's immense gravitational well. It whips around the back of the moving planet and then basically shoots back out.
Right.
And by aiming it at a very specific trajectory, the engineers ensure that the spacecraft leaches a microscopic fraction of Jupiter's own momentum as the planet orbits the sun.
So the energy is literally coming from Jupiter's movement through space.
Correct. And because it is an equal exchange of momentum, Jupiter actually does slow down.
Wait, really?
Yes, really.
But the scale of that exchange must be just incredibly disproportionate.
Oh, vastly disproportionate. Jupiter is so unimaginably massive that giving up that energy slows its orbit by an utterly immeasurable amount. We're talking fractions of a millimeter over billions of years. You could never, ever detect the change. But transferring that exact same amount of kinetic energy into a tiny 2,000-pound spacecraft, that results in a colossal speed boost. No fuel is burned by the probe to gain that acceleration. It just leverages the mass of the solar system against itself.
That is wild. The source uses this really beautiful analogy of a stone skipping across a pond. Voyager 1 used Jupiter's gravity to accelerate towards Saturn, and then Voyager 2 took it even further, using Saturn to slingshot to Uranus, and then Uranus to slingshot to Neptune.
Right.
They were just gathering velocity from each giant they passed, like they were skipping across the cosmic pond.
Exactly. And armed with that stolen momentum, they weren't just racing the clock. Their cameras and sensors were wide open. And what they were hurtling toward completely shattered our existing understanding of the solar system. I mean, we really have to consider what humanity actually knew about these places before 1979.
Yeah, let's talk about that, because if you point a high-powered telescope at the sky in the mid-70s, you are essentially just looking at faint, blurry smudges, right?
Exactly. Faint smudges. We knew they were massive planets, of course, but they lacked any kind of sharp definition. The Voyagers were about to provide our very first close-up portraits of these distant worlds, and they found systems that were far more dynamic and honestly more violent than anyone predicted.
The sheer variety is just staggering. The essay details how they looked at Jupiter and revealed that its great red spot isn't just like a flat surface feature.
No, not at all.
It's a colossal, high-pressure anticyclonic storm that is actually larger than Earth itself.
Yep.
And then they showed us the intricate, almost record groove complexity of Saturn's rings. They looked at Saturn's largest moon, Titan, and found it wrapped in this thick, hazy, orange atmosphere of nitrogen and methane.
Right. They proved that these weren't just dead, frozen spheres of gas and ice floating out there. They were active, evolving systems.
But the detail that really made me pause was their discovery on Jupiter's moon, Io. The text points out that Voyager found Io to be completely covered in active volcanoes.
Oh, that was huge.
It's amazing. This was the first time active volcanism had ever been seen anywhere beyond Earth. But what I don't fully grasp is the actual mechanism. Io is a tiny moon sitting in the absolute freezing depths of space, hundreds of millions of miles away from the warmth of the sun. Why on earth is it hot enough inside to have erupting volcanoes?
Well, that is the crucial aha moment of the Jupiter encounter. It all comes down to a phenomenon called tidal heating.
Tidal heating, so like ocean tides on Earth.
Similar principle, yeah, but applied to solid rock instead of water.
Yeah.
So Io is caught in this massive gravitational tug-of-war. On one side, you have the immense crushing gravity of Jupiter just pulling on it.
Okay.
And then on the other side, you have the gravity of Jupiter's other large moons, specifically Europa and Ganymede, pulling it in the exact opposite direction. So as Io orbits, it is literally being squeezed, stretched, and distorted by these competing gravitational forces.
Wait, so the moon is physically bulging out of shape?
Yes. The solid ground of Io bulges up and down by over 300 feet as it orbits.
300 feet of solid rock moving. That's insane.
It is. Now, think about if you take a metal wire, like a paperclip, and you bend it back and forth rapidly in your hands. What happens to the metal at the bend?
Oh, it gets hot, like really hot.
Right. That is internal friction. So the immense friction from all that solid rock grinding and stretching inside Io generates intense heat. Enough heat to completely melt the interior of the moon, forcing magma out to the surface. Voyager didn't just find volcanoes. It discovered a brand new geological mechanism for heating a world.
Oh, wow. That makes so much more sense now. And while Voyager 1's path took it upward and kind of out of the planetary plane after Saturn, Voyager 2 capitalized on that rare alignment to push onto Uranus and Neptune.
Yeah, get going.
And almost 50 years later, Voyager 2 is still the only spacecraft humanity has ever sent to visit those two planets.
And its findings there were equally paradigm-shifting, honestly.
Yeah.
At Neptune, which is a planet so far from the sun it receives barely any solar energy at all, Voyager 2 recorded supersonic winds tearing through the atmosphere at over 1,000 miles per hour.
1,000 miles per hour.
Yep. And on Neptune's moon, Triton, it found active geysers erupting into space.
Okay, wait. Geysers on Triton. If it's even farther out than Io, and much, much colder, what is actually erupting? Because it can't be magma, right?
Right, it isn't magma. It's a process called cryovolcanism, basically, cold volcanoes.
Cold volcanoes.
Yeah, the surface of Triton is essentially just deep frozen nitrogen. And the Voyager data suggests that the faint sunlight penetrates the surface ice, heating up a dark layer of material underneath. This turns the frozen nitrogen into a high-pressure gas that eventually ruptures the ice crust, and it shoots plumes of dark dust and nitrogen gas miles into space.
That is phenomenal. So you have two small probes carrying these ancient computers, and during just a handful of brief flybys, they completely rewrote the science textbooks.
They really did.
They transformed four distant, blurry smudges into real, complicated worlds driven by tidal heating, supersonic winds, and cold volcanoes.
But, the planetary flybys were just the primary objective. They didn't hit a wall after Neptune. Physics dictates that an object in motion stays in motion. Right. Right.
So without atmospheric friction to slow them down, their trajectories carried them onward. They just kept coasting. And this takes us from the charted solar system into a completely different environment.
Yeah, the text refers to this as the second stranger chapter of their journey, leaving the solar system entirely. But to really grasp what that means, we need to clarify what the boundary of the solar system actually is. Because it's not just a line on a map past Pluto.
No, it is a physical, measurable boundary created by our sun. Because we naturally think of space as this perfect, empty vacuum, right? But the space inside our solar system is actually filled with a constant outward stream of charged particles and magnetic fields blown out by the sun.
Okay.
This stream is called the solar wind.
So the sun is continuously exhaling this plasma wind in all directions.
Constantly exhaling. And the solar wind is pushing outward at over 1 million miles an hour. It inflates a vast protective bubble around all the planets. That bubble is called the heliosphere.
The heliosphere, got it. And for decades after they passed the outer planets, the Voyagers were still sailing through this bubble, firmly within the sun's magnetic sphere of influence. But eventually, that solar wind starts to lose its strength as it pushes against the interstellar medium.
And the interstellar medium is?
Oh, that's just the gas and dust that exists in the open space between the stars.
Okay, so the essay uses a really great porch light analogy here that I want to adapt for you, the listener, based on what you just explained about the physics. Imagine you are inside a warm, brightly lit house on a freezing winter night.
I love this analogy.
It's so good. The heliosphere is like the glow of your porch light. You walk out the front door, across the yard, and you are still bathed in the glow of the house. That's where the planets are. But as you keep walking out toward the dark woods, the light begins to fade.
Right, and that fading light is a perfect representation of a region called the termination shock. That's where the solar wind abruptly slows down as it encounters the heavy pressure of interstellar space.
Right, so eventually you step past the very edge of the porch light's reach. You hit a definitive border where the wind from the dark woods finally overpowers the warmth of your house, and suddenly you're just out in the freezing, totally dark wilderness.
And that definitive border is called the heliopause. It is the exact boundary where the outward pressure of the solar wind is perfectly balanced by the inward pressure of the interstellar medium. And after decades of traveling, Voyager 1 actually reached that invisible border. In 2012, it pierced the heliopause and became the very first human-made object to cross into interstellar space.
Into the space between the stars?
Yes. And Voyager 2 followed, making its own crossing into the interstellar medium a few years later in 2018. It is a profound milestone. A machine built by human hands had finally left the sun's protective bubble and entered the wider ocean of the Milky Way galaxy.
See, what really bends my mind about this milestone isn't just the physics, it's the sheer scale of the distance we are talking about here.
The scale is almost impossible to intuit, honestly. We have to measure these distances not in miles, but in light hours. And, light travels at 186,000 miles per second.
Which is fast.
Very fast. It is the absolute speed limit of the universe.
And even at that speed, the radio signals that these spacecraft are sending back right now take an agonizingly long time to reach our antennas here on Earth. The essay notes that for Voyager 1, a single ping takes over 22 hours to arrive.
Just think about that for a second. Over 22 hours traveling at the speed of light.
It's crazy.
And yet, from that unimaginable abyss, using a 1970s radio transmitter that literally operates on less power than a refrigerator light bulb, they are still successfully beaming back data. They are literally telling us what the plasma environment of the interstellar ocean feels like today.
Now, knowing that these spacecraft were heading into an infinite, timeless void raises an entirely different kind of question for the creators. Because in the vacuum of interstellar space, there is no wind, no rain, no oxygen to rust the metal.
Nothing to break them down.
Right. So the engineers realized that these probes were going to physically outlast the mountains on Earth. They will very likely outlast human civilization itself. So they faced this profound philosophical dilemma. If you are sending a machine into eternity, what you pack.
Exactly. If there is even a microscopic non-zero chance that in some distant epoch, millions of years from now, another intelligence might intercept this craft.
Yeah.
What is the message you want to leave them about who we were?
So the committee tasked with answering that massive question was led by the astronomer Carl Sagan. And their solution was a cultural payload known as the Golden Record.
It's so iconic.
It is. It is a physical 12-inch gold-plated copper phonograph record designed to survive for 1 billion years in space, and it is just bolted right to the side of both spacecraft.
It was really intended as a portrait of humanity. The cover of the record features these etched instructions on how to physically build a stylus to play it, along with a map using galactic pulsars to show exactly where our sun is located in the Milky Way. But the contents of the record itself are what truly resonate.
Yeah, they encoded 115 images of life on Earth. They included spoken greetings in 55 different human languages, and they dedicated a vast amount of space to music. I mean, everything from classical pieces by Bach and Beethoven to Navajo chants and even rock and roll with Chuck Berry.
But beyond the music and the languages, they included a curated selection of audio designed to represent the planet itself.
And this is the part that I find so moving, honestly. You have this incredibly cold, highly engineered feat of astrophysics, right? Titanium, nuclear generators, and gravity assists.
Yeah.
And bolted to the side of it is the audio of rain, wind, and thunder. There's bird song and the haunting clicks of a whale. And then there are these remarkably intimate human sounds. The sound of mother's kiss, the sound of a human heartbeat.
It creates such a poignant contrast. The spacecraft represents our mathematical and technical prowess, sure, but the record represents our emotional and biological reality.
It is literally a message in a bottle cast into a sea of stars. And the engineers did this knowing full well that the vast emptiness of space means it will almost certainly never be found. It wasn't just a science experiment. It was a deeply hopeful expression of our existence.
Absolutely.
You just have to wonder, for anyone listening to this deep dive right now, if you were on Sagan's committee, what one sound would you want to represent us to the universe?
Oh, that's a tough one. It really forces you to distill humanity down to its absolute essence.
It does. Now, before the Voyagers completely lost sight of us in the darkness, they executed one final maneuver that captures that exact same philosophical weight. We've explored the message they carry out to the universe, but we really have to discuss the final visual message they sent back to us.
Yes. This occurred in 1990. Voyager 1 had been flying for 13 years and was roughly 6 billion kilometers away, sailing far, far beyond the orbit of Neptune.
And Carl Sagan, who spearheaded the Golden Record, goes back to NASA and lobbies for them to turn Voyager 1's camera around.
Which was a big deal at the time.
Huge deal. He asked them to point it back toward the inner solar system and take one last series of photographs, including a shot of Earth. Because from 6 billion kilometers away, Earth doesn't look like a giant blue marble anymore.
No, not at all. In the resulting image, which is famously known as the pale blue dot, Earth barely registers.
The essay describes the photograph so vividly. You see this vast, overwhelming ocean of black space intersected by a scattered ray of sunlight that just happens to be hitting the camera lens. And suspended right in the middle of that sunbeam is a single tiny point of light. It is less than a single pixel in size. That pale blue dot is us.
It's incredibly humbling. Sagan's reflection on that specific pixel of light remains, I think, one of the most powerful pieces of scientific prose ever written.
Definitely. He observed that on that tiny speck is everyone you love, everyone you know, everyone you ever heard of, every creator and destroyer of civilization, every king and peasant, every couple in love. The entirety of human history, all of our joy and suffering, happen right there on a mote of dust suspended in a sunbeam.
Just a single pixel.
Right. And he argued that seeing our world reduced to that single pixel underscores our immense responsibility to deal more kindly with one another and to preserve and cherish the only home we've ever known.
The mission provided us with unparalleled data about gas giants and the interstellar medium, but arguably its greatest contribution was that vital shift in perspective. But, bringing our focus back to the reality of the present day, this incredible journey is nearing its functional end.
Right. The source notes that the Voyagers are finally running out of power. Because they are way too far from the sun for solar panels to work, how are they actually powered right now?
So they are powered by radioisotope thermoelectric generators, or RTGs.
RTGs, okay.
Essentially, they run on the heat generated by decaying spheres of plutonium. But after nearly 50 years in space, that plutonium has decayed significantly. The generators are producing less and less electrical power each year.
So the engineers at NASA are basically having to play this delicate game of survival.
Exactly. To keep the core communication systems and vital sensors alive, they are systematically shutting down everything else. They turned off the cameras long ago, and now they are shutting down the onboard heaters, letting the remaining scientific instruments literally freeze in the cold of space, all just to save a few watts of power.
But the reality is just a math problem at this point. Within the next few years, the RTGs simply won't generate enough wattage to power the transmitters. The spacecraft will eventually fall completely silent. No more pings from the dark.
Right. They will lose their voice, but they will not lose their momentum. Physics guarantees that. Without friction to slow them down, they will continue to coast outward at over 35,000 miles per hour. Silent, gold-plated, and completely intact, they will just drift through the Milky Way for millions upon millions of years.
Long after The Last of Us is gone, they will just be out there. A testament to curious, hopeful creatures who looked up, wondered what was in the dark, and just built a machine to find out.
It is the ultimate enduring legacy of human curiosity.
It brings my mind back to where we started today. We opened by discussing the computing power of your car key fob.
Right.
We recognize how incredibly fast our technology has advanced since 1977. And it leaves me with one final thought, something that's not explicitly in the essay, but something to really ponder for a second. We instinctively assume that the golden record is meant for extraterrestrials, right? We assume it's for some alien intelligence to find. But what if the Voyagers are never intercepted by aliens at all?
Well, given the vast emptiness of space, that is statistically the most likely outcome.
Right, but think about the trajectory of human innovation. What if humanity actually survives its adolescence? What if over the next thousands or millions of years we continue to evolve and we eventually crack the physics of faster-than-light travel?
Oh, I see where you're going with this.
The universe is unimaginably vast, and Voyager is incredibly small and silent. The first people to eventually stumble upon this ultimate message in a bottle drifting out in the dark might just be our very own distant descendants.
Wow. They could be traveling out into the stars only to unexpectedly cross paths with our civilization's own childhood footprints.
Exactly. Imagine humanity, millions of years in the future, finding a golden record bolted to a machine with less computing power than a piece of plastic, and realizing this is the fragile, ambitious beginning of where we started.
That's a wonderfully grounding thought to leave off on.
Thanks for joining us for this deep dive. Keep looking up, and we'll catch you next time.